Okay. Almost forgot to put the microphone on. So we're going to do the ladder problems here. Ladder problems. So let's see, there in the 50s, 49 and 50s. So the first one is 49. And it says that we have an unusual die that has the numbers 2, 2, 3, 3, 5, 8 on the 6 faces. 2 of these dice are rolled, and the 2 numbers on the top faces are added. How many different sums are possible? So what you can do is you could do a table. You still have 6 choices, but some of them are the same. So I think I can make my table as such. So we just write down the 2 dice. We'll call it dice 1 and dice 2. So it's 2, 2, 3, 3. And apparently I didn't make my table big enough. Let's try again. That's supposed to be 7 by 7. Here we go. So let's try it again here. Dice 1, dice 2, 2, 2, 3, 3, 5, 8. So we'll just add these together. So all I'm doing is adding these 2 numbers to get the one at the intersection of them. Okay, so those are all the additions. 8 plus 2 is 10, 8 plus 2 is 10, 8 plus 3 is 11, 8 plus 3 is 11, 8 plus 5 is 13, 8 plus 8 is 16. So what we'll do is we'll just circle the numbers. And so you have 4, 5, 6, 7, 8. There's no 9, 10, 11. There's no 12, 13, there's no 14, 15, and 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 sums. So that is problem 49. I'm trying to think if there's any other easier way. Because I think if you wouldn't need to make quite as big a table if I just did 2, 3, 5, and 8 in both directions and added those together. I think I would still get the same result. So let's just do that, because they're repeating things. So I'm going to do it 5 by 5 in this case, and only include ones that are different. I bet I'll still get 9 as the answer. So again, these are the 2 die, and you have 2, 3, 5, 8, 2, 3, 5, and 8. So now we add these together. 2 plus 2 is 4, 3 plus 2 is 5, 2 plus 5 is 7, 8 plus 2 is 10, 5, 6, 8, 11, 7, 8, 10, 13, 10, 11, 13, 16. So those are the sums of these two. Again, I'm going to circle. So my smallest one is 4, 5, 6, 7, 8. There's no 9, 10, 11, no 12, 13, no 14 and 15, 16, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I could have simplified things from that perspective. Okay, 51. The number of games in the test tournament. 50 people enter a single elimination chess tournament. If you lose one game, you're out. Assuming no ties occur, what is the number of games required to determine the tournament champion? I swear I've done this before. I've recorded this before, so I'm not really sure where it is. But anyway, so if you think about the basketball tournaments for March, the NCAA tournament, they originally were 64 teams, and it was also a single elimination tournament. And you chose 64 because you start with 64, and then you have 32 winners, and then you have 16 winners, and then 8 winners, and 4 winners, 2 winners, and then finally 1. And if you add all those up, so let's say you start with 64, you get, so originally from the 64 initial teams, you get 32 games. So this is teams, this is games. The second round, you have 32 left, so there's 16 games, since you need 2 teams to play a game. Next round, you have 16 teams or 8 games. Next round, you have 8 teams or 4 games. Then you have 4 teams and 2 games, and 2 teams and 1 game. You add all these up, and you'll get 63. So the number of games played is 1 less than the number of teams. So in this case, you have 50. So that is not a power of 2. So you're going to have like an initial tournament to reduce it down to. So you're going to start with 50 teams. You're going to have so many games. So let me remember how to do this, because I do remember doing it before. So you're going to have like a preliminary, and then the winners from this are then going to feed into something which ultimately has to be something like this, where you finally come up with a power of 2. So I'm going to assume the next round, and you're going to need 32 teams. And so the question is, how many games do I have here so that when I get the result of this, so let's say this X teams play here, they're going to be 32 teams in the next round. Okay. And what else do I need to know here? So there are going to be a certain amount of teams that get a bye, and that's going to be 50 minus X. Okay, so yeah, I think that's going to work out. So what I'm going to do, the 32 teams has to be equal to the number of teams that get a bye plus X divided by 2. And that's because this X teams play, but only X over 2 teams actually make it to the next round. So this should be the equation that will figure out how many games I have to have here. At this point, from my previous little example, I know that there are going to need to be 31 games associated with 32 teams at this next level. So my total is whatever X is, total games, is going to be equal to 31 plus x, because I'm going to need 31 to do that. Okay, so let's figure out what x is. So I'm going to multiply both sides. Go down here, I'm going to multiply both sides by 2 to get rid of this fraction. So I'll get 64 is equal to 50 minus x, whole quantity times 2 plus x. So 64 is equal to 100 minus 2x plus x. And if I subtract 100 from both sides, I'll get negative 32 is equal to negative x, or x is equal to 32. So let's see if that works or not. So here we got 32 teams. That means I've got 50 minus 32 teams here, which is 18. Okay. Now if I take the winners, so from here I'm going to have 32 divided by 2, which is 16. And just going to take a second here. I'm going to plug in my headphones. I got okay, so here we go. I think I did something wrong here, because let me think here, make sure I'm doing this right. So I'm going to need 32 teams. And actually, once I have 32 teams, that means I've got 16 games. So it's 16, the number here, plus the number of games that I have there. So let's see what we got here. So the number of teams I need here is 32. X is a number I have in the prelim. Divide that by 2, and I add that to 50 minus x. I'm going to pause for a second here. Okay, I found my error here. I just can't subtract. So this is 36. So if x is 36, we'll fix that. So if x is 36, then 50 minus x is 50 minus 36, which is 14. And actually you need 15 games at this point. Is that right? No, you need 31 games. It's always one less. So in this case, we had 64. We need 63 games. So the same thing applies. So you need 31 games to do this sub part. And then we had 36 teams here, which means 18 games as a prelim. Okay, so you take 36 teams, that leaves 14 teams that got to buy. Half of 36 teams is going to be 18 games. With the remaining 32 teams, which I now have 18 from here and 14 from there, adds up to 32. I'm going to add 18 plus 31, and 18 plus 31 is 49. So it doesn't matter whether you have a nice multiple or power of 2, it always works out that the number of games to play a single elimination tournament, even if you have to have buys, is 1 subtracted from the number of teams in the league, which is interesting. Okay, what else we got next? 52, okay, 52. How many positive integers less than 100 have the sum of their digits equal to a perfect square? So let's just look at that as an example. So it's how many positive integers? So positive integers 1 to 99. And if we add those up, 1 plus 0 is 1, and this is 18. And so the maximum number we could get would be 18 as far as the sum. So the perfect squares that are less than 18 are 1, 4, 9, and 16. So those are the 4 perfect squares that are less than 18. So then you can find out for each one of these how many what numbers add up to these between 1 and 99. So we did this in class. For 1, you can have 0, 1 or 1, 0. So those are the 2 numbers that add up to equal 1. So the sum is equal to 1. Okay, we need to do the same thing for 4. So you'll have the same 2 choices. You'll have 0 and 4 and 4 and 0. And then you'll have 3 and 1 and 1 and 3. And then you'll have 2 and 2. So those are all, so we have 2 here for this first case. We have 1, 2, 3, 4, 5. 5 for the number 4. For 9, you have 0, 9, and 9, 0. You have 1, 8, and 8, 1. You have 7, 2, and 2, 7. You have 6, 3, and 3, 6. And you go to 4, 5, and 5, 4. And I think that's it. So those are the 2-digit numbers that add up to 9, 2, 4, 6, 8, 10, 10, and then finally 16. So let's start at the large numbers. So you get 9 and 7, and 7 and 9, and then you would have 8 and 8. If you go to 7, there's nothing. Well, we already have 7, and then if you have 6, it's just not big enough. So in this case, you have 3. So if you add all those together, you get 10 plus 5 is 15 plus 3 is 18 plus 2 is. So I figure there's 20 of them, and that is the correct answer. Okay, and then the last one I think we're doing here is 57. Actually, I think we had 50. We'll assign 54 as well. So 54 says integers containing the digit 2. So what you have is let's think about this. This is how many? Between 100 and 400. Okay, so let's start from the 100s. So you have 102, you have 112, you have 120, 20, you have 120. Okay, 21, you have 122, 123, 124, 125, 126, 127, 128, 129. So, and then if you go to 130, you've got 132, So it looks like we have 1 per decade. So that's going to be 10 for the hundreds. And the same thing is going to be true for the 300s. So this is the 200s. You've got 10, well, except we're going to have more when we get to the 20s. So except for the 120s, we're going to have 1 occurrence each decade. So that's going to be 9. 9 plus, then you're going to have the 20s. So you're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you've got 10 that are in the 20s. So there's 19 in the 100s. Sorry, that was the 100s. Now in the 200s, all of them are going to have a 2, right? So 201, 202, 203. So there's actually 100 of those. And then the 300s should be like the 100s. You should have 9 in the decades except for the 20s. And then you should have 10 in the decades. So when you add that up, you get 238 numbers. How did I get 238? It's 138. 100 plus 19 plus 19 is 138, which is the correct answer. So I didn't have to list them all. I kind of recognized a pattern, and I went from there. And then the final one is 57. So what is this thing? For exercise 57, for example 7, how many different settings could Pamela choose in each case? Okay. So you got 4 switches, and there's no restrictions. So in that case, you basically have, it's kind of like switching or flipping a coin. So you would end up, you could do a tree diagram. Since we've learned about the fundamental counting principle, it's just going to be 2 times 2 times 2 times 2 times 2, which is 16, is the answer for 57.